So, today we start a new lecture, lecture 25. So, in which we will discuss the remaining part of ionic solids structures. Ionic solids are nothing but ceramics. So, we will talk about remaining cubic structures and non-cubic structures. So, let us just recap about the last class. Last class we did so in the last class we talked about FCC structured ceramics, that is we talked about mostly spinel structures which are based on Ab2O4 kind of compounds, and these spinels are in two forms. One is normal spinel and second is inverse spinel. So, normal spinel, A goes to tetrahedral, B goes to octahedral, and then oxygens make a FCC lattice. In case of inverse, your A, B go to octahedral, and one B goes to tetrahedral, and oxygen makes a FCC lattice. So, normally why spinel structure is important, because many aluminates and many ferrites make this structure. So, typically aluminates will make normal spinel structure typically, and typically ferrites will make inverse spinel structure. So, this is the difference between the two, and then we looked at the perovskite structure, which is based on AbO3 formula unit, and this is compounds such as barium titanate, strontium titanate. Let me just thicken the strontium titanate, calcium titanate, and so on and so forth. They follow this kind of structure, and this is basically based on a non-FCC packing. So, here in the unit cell oxygens go to face centered sites, barium goes to corners, cell corners, and titanium goes to the center of the, B goes to the center of the cell. So, this is A, this is B, and this is O. This is typically, now it exists, perovskites exist in both cubic and non-cubic forms. What I have shown you here is cubic. So, it is basically a primitive cubic lattice, but many of these materials are ferroelectric in nature. So, they undergo your Curie transition at a temperature called as Tc. So, let me now come to that particular aspect. So, what we talked last time was that AbO3 is primitive cubic with motif being at A at 0 0 0, B at half half half, and oxygen at half half 0, half 0 half, and 0 half half. But many of these compounds, AbO3 based compounds such as barium titanate, calcium titanate, lead titanate, etc., if not and bismuth ferrite, many of these are ferroelectric in nature. So, these are all ferroelectric. Okay. Now, ferroelectric materials have a property which is called as they undergo a Curie transition, that is their dielectric constant varies as a function of temperature, and it undergoes through a maxima, anomalous increase at a temperature called as Tc. This Tc is called as Curie transition. Now, typically so this in this diagram, below Tc these materials are in ferroelectric state, and above Tc they are in non-ferroelectric, that is called as paraelectric state. Now, what happens is, for example, in case of barium titanate at about 105 degree centigrade or so, I can't exactly remember, it's about 100, it's above 100, it's about between 105 and 100 and 120. So, above this Curie temperature of barium titanate, its structure is cubic. So, what we followed is perfectly replicated there, but below Tc the material has a tetragonal structure. So, the unit cell, which is a cube, now converts into a, so below Tc this length is slightly larger than these two lengths. So, this is A, this is A, this is C. So, C is greater than A, there is some C by A ratio which unit cell will have. So, many of these perovskites in the ferroelectric state, in fact all of them, they are non-cubic, which is required by the, which is necessitated by the requirements of ferroelectricity. Ferroelectricity cannot occur in cubic compounds, but at higher temperature they become cubic. So, this is a difference between perovskite and cubic perovskite and non-perovskite cubic perovskites. So, many of them, so cubic perovskites above Tc, the structure will be typically cubic. Below Tc there will be some distortion, it is a very minor distortion in the unit cell, and this minor distortion leads to non-cubic structures. So, these could be tetragonal, rhombohedral, and so on and so forth. It is just a slight distortion in the unit cell which makes the cubic symmetry to go away. So, there is no cubic symmetry. So, this is the perovskite structure. Now, next in this series is called as Reo3 structure. Now, Reo3 is the parent compound. Other compounds which follow this structure, for example, oxides such as WO3, MOO3, they tend to follow this. So, in this compound, the stoichiometry, as you can see, is MX3, and basically this structure is like this. So, you can see that here M is a in this kind of structure, M is plus 6 ion, and you have 3 oxygen which are 2 minus, and there are 3 of them. Okay. The atomic positions happen to be M at 0 0 0 and X at half 0 0 kind of positions, half 0 0, 0 half 0 and 0 0 half type of positions. It is a primitive cubic lattice. So, this is M. Again this now we will see the coordination. I have not told you the coordination. This is the position of So, what is the coordination of M in this case? M's coordination is, if you go in this direction, if you go in this direction, if you go in this direction, you will have one O here, here and another O here. So, it will be 6-fold coordination. So, coordination number of, so what is the coordination number of oxygen in this case? You can do the bond strength check, but you can see the stoichiometry is 3 times. So mx3 1:3, it's got to be 2. So can you correlate this structure with AbO3 structure? We can correlate with that. This structure is very similar to AbO3 with, so if you look at AbO3, we drew AbO3 in this form, right? So where is now A? A is missing here. So this A is missing. It's a perovskite. It can be considered as a sort of perovskite structure with A atom missing. So it's just BO3, all right, just BO3. So this is what the structure is like. So coordination of M is octahedral, coordination of oxygen is linear. Okay, so this is the coordination, and the examples I have given to you. This is an important, these are all important materials because you can see the structure is very open now, right? You can see that there is a big void at the center of the unit cell, and this big void in the center of the unit cell allows these materials to carry on defects, and they provide good defect migration, and they can also carry out, they can also consist of impurities. So these materials, for example, tungsten oxide is used as a sensor, it's used as a electrochromic material, materials which change their color when they are applied electric field. So similarly, moly oxide is used for a lot of electronic applications. So the structure or the open structure of this material helps in that, achieving those attributes. So now let's look at another structure which is again cubic based structure, which is called as CsCl structure, and this structure is followed by cesium chloride is a parent compound, but it is followed by compounds such as silver bromide or silver iodide and so on and so forth. So again you can see it is a AB stoichiometry where, or Mx you can write Mx, where M is to X is 1:1, which means both the ions will have similar coordination, that is for sure. So these materials also turn into rock salt structure at higher pressures, but at lower pressures they remain as a cesium chloride structure, and a lot of halides adopt this kind of structures, bromides, iodides, chlorides of basically larger ions, the ions which are bigger, which require larger coordination, they adopt this structure. So in this structure, the structure is, so we basically have, based on radius ratio, we have cubic coordination, of cations, which means coordination number is 8. This also results in coordination number of 8 for anions if you apply the bond strength rule. So the structure is something like the following. These are chlorine atoms, and the cesium atom goes right at the center of the unit cell. So this is chlorine, this is cesium. So these are all, of course, when you make the ball model they touch each other, but for the sake of clarity we have drawn them as separate. So this is a primitive cubic lattice with motif being as cesium at cesium at half and chlorine at, you can write the other way around as well. You can write the motif as chlorine at half and cesium at 0,0,0, because you can put the unit cell wherever you want. So if you draw the plan view, it will look something like that. And this will be your So, this is at half, this is at 0 1. So, you can consider each of these being connected to this ion. So, it is kind of dumbbell shaped structure. So, you can make them unit cell. Let us say if you make the unit cell here, it will consist of one dumbbell of one of these, right. So, maybe you can consider this, create the bond between this and that. Okay. So, let me see if I have a picture to show you. So, this is how rhenium oxide structure would look like. So, this is the first representation in which you have B atoms and the oxygen. You can make slightly elongated structure, show the octahedras clearly, and if you make the polyhedral view, it looks like as if this is the polyhedral view of Reo3 structure. So, this is the cesium chloride sort of structure. You can say that these are the sort of dumbbell shaped structures. So, these are all chlorine atoms, these are all cesium atoms. Okay. So, now we will move on to another category of materials which are ceramics, basically ionically bonded ceramics, which are non-cubic compounds. They are not hexagonal, they could be orthorhombic, they could be tetragonal, but they contain perovskite units. The perovskite units are inbuilt between them, or they contain some other, they may contain, for example, sodium chloride units, or so on and so forth. Now, many of these compounds happen to be very important for a lot of technological applications. Okay. So, one such structure is yttrium barium copper oxide. Yttrium barium copper oxide is a superconductor, YBa2Cu3O7 minus X. Now, this material is basically, if you look at the parent compound of this material, as drawn on the left is Y3. So, the parent compound is Y3Cu3O9. It has a tetragonal structure. In this unit cell, you can see it is made up of 3 unit cells of YCuO3. So, you can see that Y3Cu3O9 or YCuO3 3 times, right. So, you have 3 unit cells stacked on top of each other, which are perovskite in nature. The way it is made superconducting is by first doping it with barium. So, what barium does is that barium replaces 2 of the yttrium ions. So, one in the bottom unit cell, another in the top unit cell. So, this leads to YBa2Cu3 3 plus. This is Cu3 plus, by the way, not Cu2 plus. Okay. Now, since barium has less oxygen with it, because it has valence of only +2, there is oxygen deficiency. So, oxygen deficiency is now, it results in O8. Okay. So, you can see there are some vacancies of oxygen, some of the oxygens had disappeared. So, these oxygens which were present here, they have now disappeared. So, you have oxygen vacancy, oxygen vacancy, oxygen vacancy, oxygen vacancy. It is not a vacancy in the type of defect, it is just there is no oxygen there now, okay, because of stoichiometry. You further reduce Cu3 plus to Cu2 plus, so that it becomes YBa2 Cu22 plus Cu3O7. So, you have 2 of Cus and Cu2 plus, 1 of Cu and Cu3 plus, and as a result oxygen becomes 7. So, when you do that, the reduction is not complete, it's not stoichiometric. So, you end up having 7 minus X, and this 7 minus X state is the superconducting state. So, you have many more vacancies of oxygen. This is oxygen, empty oxygen site, these are empty oxygen sites, these are empty oxygen sites. So, this is a perovskite unit based structure which is modified into a superconductor. So, you still have the basis is still perovskite, it is just that it is a modified perovskite. So, this becomes so it has it does not have the typical octahedral coordination you will have. So, for example, oxygen the copper in these positions, it has 5-fold coordination because the one oxygen on top has gone missing, which was present earlier. So, instead of 6-fold coordination, you end up having 5-fold coordination. Here because you have oxygens missing on this side as well as on this side. The oxygen, the copper is surrounded by now 4 oxygen atoms. So, you have 4-fold coordination, you have 5-fold coordination instead of typical 6-fold coordination as you would have in perovskites. And it is along these Cu chains the superconductivity prevails. So, superconductivity is along those directions. So, this is one interesting example of perovskite based structure. It is not exactly perovskite because perovskite is just one unit, but it contains multiple perovskite units in it. Second structure is again a superconducting oxide, which is lanthanum strontium copper oxide. In this it has a, now by the way, yttrium barium copper oxide was a superconductor with a transition temperature of 92 Kelvin. This was the first superconductor when it was discovered which had a transition above liquid nitrogen. See, most of the superconductors had transitions lower than liquid nitrogen. That made that, so if you wanted to use superconductors in any application, you would have to use liquid helium. Liquid helium is far more expensive and difficult to manage as compared to liquid nitrogen, which is far more cheaply available and reduces the cost of operations. So, this discovery was a major discovery in the area of superconductivity because 92 Kelvin was higher than liquid nitrogen. So, you could have a superconducting wire at 90 Kelvin without needing liquid helium, which was a great achievement.
Those materials also, as they are perovskite, we can say they are perovskite.
They are not perovskites as you see. Perovskite is just AbO3 structure. This is based on AbO3 structure, but it has a, you can say it's a triple perovskite. It's not a single perovskite, it's a triple perovskite.
So they have some properties like ferroelectric also?
Many of the, I'll show you, I'll come to some of these compounds. So, for example, lanthanum strontium copper oxide, this is also a superconductor. Basically, the parent compound is lanthanum copper oxide, in which strontium is doped at the site of lanthanum. So, as a result, you change the stoichiometry of this material to some extent. So, this will change, the oxygen stoichiometry will change. This has a Tc of 35 Kelvin. This again is built of perovskite layers. So, you can see this perovskite layer, this is the copper atom, this is the lanthanum atom, and this is the oxygen. Copper is the smaller atom, lanthanum is the bigger atom, and it has these zigzag kind of perovskite layers. You have one perovskite layer, another perovskite layer is shifted by half 110 vector. So, it has this one perovskite layer, shift another perovskite layer, and so on and so forth. So, overall if you look at this, together they make a NaCl layer. It is very interesting structure. So, it has this layered structure. The first layer is copper oxide, second layer is AO4, A could be strontium or lanthanum. So, copper oxide layer, AO4 layer, A4O layer, CuO2 layer, A4O layer, AO4 layer. It looks complicated, but it is fairly simple layered arrangement, but the layers are shifted. The position of ions in these layers is such that you have these alternating sodium chloride layers, and in between you have these perovskite layers. So, you can see that perovskite layer containing CuO6 octahedra. So, you have this copper atom and then you have these oxygen atoms surrounding in the octahedral manner. So, this is a layered structure which is a blend of perovskite and NaCl sort of structure. So, you can't see, it is not apparent when you look at the tall unit cell, but when you look at it closely you can see that there are similarities with the perovskite structure as well as with the NaCl structure. So, some of these structures which look very difficult to just to visualize, they can be remarkably simple. So, just stacking of layers CuO2, AO4, A4O, CuO2, AO4, A4O, AO4, just go in that sequence. Now, the third structure in this category that we will talk about is ferroelectric bismuth titanate. Now, this is a ferroelectric compound Bi4Ti3O12. This is not a perovskite structure, but it does contain perovskite units. Now, this belongs to a family of what we call as aurivillous compounds, aurivillous phases or compounds. So, you have bismuth titanate, you have strontium bismuth, SrBi2TO2O9, and some other oxides which belong to this category. These are mostly bismuth containing compounds. So, in these compounds what happens is that you have perovskite layers which are sandwiched between the bismuth oxide layer. So, in between you have Bi2O2 layers. So, these are Bi2O2 layers, you can see the purple bismuth and red oxygen atoms. Between the two successive Bi2O2 layers you have 3 perovskite layers. So, first perovskite layer, second perovskite layer, third perovskite layer, in which titanium is octahedrally coordinated by oxygen. However, these perovskite, since these are in these materials, this is the tetragonal structure. In these materials there is significant distortion of octahedra. Octahedras are not all running straight. There is a bit of twisting and rotation of octahedra. You can see that this octahedra is going this way, this octahedra is going this way. So, there are different axes along which they tilt and twist. So, this rotation or distortion of octahedra leads to ferroelectricity. Ferroelectricity does not occur in symmetric compounds, it only occurs in non-symmetric compounds. So, this tilting and distortion of octahedra brings about ferroelectricity. Similarly, in barium titanate and other compounds, cubic does not have any dipole moment because all the vectors cancel each other. It is only in the non-cubic form, in tetragonal or rhombohedral or other forms, in which octahedra is slightly distorted, and that distortion gives rise to ferroelectricity because of finite dipole moment. So, and there are other factors as well, but that is very simple. So, these are all perovskite layers, 3 of them. 3 perovskite layers sandwiched between successive Bi2O2 layers. So, it is not exactly a perovskite structure, but it is based on perovskite units. So, many of these compounds, they may contain 3, 5, 7, various possibilities are there. So, it is a whole series which can be built upon these perovskite units. So, just the number of you change the number of these layers and you can make different formulas of these aurivulus phases. So, these are 3 types of compounds which basically have these structures. So, let me go back to my this thing. So, among the non-cubic structures, the first one was YBa2Cu3O9, which converts to YBa2Cu2, this is 2 plus, this is 3 plus, O7 minus delta. So, this is the superconductor, this contains perovskite units. Then you have La1 minus X SRX CuO4, this is again a superconductor. So, these are superconductors. Then you have compounds such as Vi4 Ti3O12, SrBi2 Ta2O9, these are all ferroelectric. They contain perovskite units in them. Okay. So, this is the there are a lot of manganites as well. For example, lanthanum strontium manganese oxide LSMO. This is also so this is LaSrMnO3. This is again a magnetic oxide, it is a colossal magnetoresistive oxide. These are also perovskite structured compounds. So, these are some of the cubic and non-cubic structures. In the next lecture, we will look at the ionically bonded ceramics or ceramic structures which are based on hexagonal close packing of oxygen atoms, and because that is also an important category of materials in ceramic structures. Okay. Thank you.